we go. All right, so going back to chapter 5, I believe we got to the point where we were talking about these graphs. We were talking about bar charts and how to read them, whether they're single or if they're stacked like this. So, for example, what was the absolute difference in Trump voters who plan to vote in person on election day compared to the percent of Biden voters who plan to vote in person on election day? So, according to this graph here, Trump voters in person on election day would be 50%. Biden would be 20%. So this would be an overall absolute difference of 30%. Now the percent difference in Biden voters who plan to vote by mail compared to the Trump voters who plan to vote by mail. So that would be the yellow absentee or mail-in ballot. So that's 51% for Biden. And then 25% for Trump. So again, think new minus old over old. So new value is 51, old would be 25. Times 100. So 26 over 25 times 100. 104% difference. So being able to determine percent difference is going to be a key thing with these graphs. Any questions on what you see here? Okay. Would you say that headline is accurate for this one? Head shaking, yes, I'd say so. 47.2 to 94. That's essentially doubling what it was before. If we really wanted to, we could figure out the actual percentage. I think 94 minus 47.2 divided by 47.2 times 100. Looks like 99.15%. Of an increase. And we could have some other types of comparative graphs, whether through lines or time series. I believe this would have been one of the last examples we looked at right before break. But essentially, percent decrease, we can get the values and then use the new minus old over old formula. When cell phones overtook landline phones, you would look for the interception around here and go to the X value. Absolute difference is just comparing data values. And then percent difference, same thing over the old value. But just wanted to refresh your memory on these different techniques here. This is another example of a stacked graph. What were the total music sales, if you had to guess, in 1980? Yeah, I'd say so. So we're going to the highest point on the graph in 1980, over to the Y value. So somewhere in between 10 and 15 billion is what we would need for that. So I'm just going to say about 13 billion. Now, in terms of the cassette sales, this is where I have to pay close attention here. Cassettes are the yellow. Yellow starts there in 1980 and ends there. Roughly, how much would you say the yellow cassette section takes up?
Like 3 billion.
Yeah, that makes sense. Just looking for the change in Y values from start to finish in just that region. So about 3 billion. Any questions on how to get specific portions of the graph there? Okay, for some reason it's not sharing my screen again. So let's try this again. Okay, good. So some other graphs would be any type of geological graph. So think map of the world, map of the United States, some other type of pictograph that uses pictures or symbols. Infographics are essentially multiple graphs or sets of data all in one display. For an infographic, think graphs on steroids, as I call it. So here's an example of one of these. Agricultural yield of cereals in 2018. So based on the color of each country, you can figure out how many tons per hectare of cereal are being produced in that country. So for example, the United States is going to be greater than 6. Whereas say we go to Australia, somewhere between 2 and 3. Another example where people are happiest or unhappiest with their lives. Glad to see that the US of A is doing pretty well there. Europe usually does pretty well on these surveys too. Here's another one. Share of adults saying they will put up a Christmas tree in 2023, whether it be a real one or a plastic tree. So most people in Germany would put the real tree. Most people in the United Kingdom are going to use the artificial tree. And then here's the infographic one. See what I mean by graphs on steroids? On this one, I can see 22 different percent values on there, describing 22 different things. But the use of the pictures there will help you slightly by distinguishing each piece. But any type of poster or think something on TV would probably use something like this to quickly get their point across. Any questions on anything in chapter 5? So again, everything in chapter 5 dealing with statistics. Next chapter, which is going to be chapter 6. For some reason, the notes aren't there, so I'll do it this way. right, so we will go to chapters. I'll give you the notes for that here. Okay. And I will say before we start this chapter, the next exam that we're going to have is going to be Wednesday next week, which is going to focus a lot on chapter 5, actually. So on Wednesday, I'll bring the reviews with me, give you some time to look at that once we finish the notes here. And then we'll go from there. But basically, chapter 5 was basically giving you all of the statistics terminology. Chapter 6 is essentially going to be the math behind all of those terms. So chapter 6 is basically going to be taking all of the things we did in chapter 5, dealing with statistics and studies and experiments, reading graphs, all of those sorts of things, and being able to characterize data. We're going to be looking for how the data is distributed or spread out. And we're going to try to get some summary statistics to quickly analyze the major trends taking place. So the first thing that many people want to know about are measures of center, typically indicating the average, which in our terms is going to be the mean. To find that, just add up all of the values you have, divided by the number of values in the data set. This is compared to median, which is the value that falls in the middle of the data set when ranked from least to greatest. Odd number of values, it's going to be a single value. If there's an even number of values, then you're going to have to look at the middle two values and take the mean of them, the average. So add the two values in the middle together and divide by 2 if you have an even number of data values. Mode is going to be the value or group which occurs most often. And then another one that's often paired with these is the range. What do you think range refers to? Lowest to highest. Yep. So the way that you calculate this, think highest value subtracted by the lowest value. So an example of this, below are some exam grades from a sample of students. Those list of scores, let's compute the following. So at your seats, let's see if you can figure out the mean, median, and mode for each of these. Give you a few minutes here to look at them. Okay, do we have any of those values yet? What do you have?
For the mean, I have 80.75.
Okay, 80.75. That matches mine.
For the mean, I have 92.5. Or wait, median. Wait, yeah,
Median 92.5.
yeah.
Just out of curiosity, so you did this kind of thing, right?
Yeah, and then there was the two, oh wait.
So,
So we're just doing this.
so I agree with the process there, but there's one little detail with this list. In order to do that, they have to be
Lowest to highest.
lowest to highest. Yeah. So if we rearrange this from lowest to highest, let's see, 62, 71, then what, 74, then 76, And I see an 80,
Wait, 79.
79. Thanks for that. So 79, then 80. Then we got 83, two 84s, 86, a 91, and a 99 in that order. So then if we cross out low, high, looks like we got 80 and 83 in the center. So then what do we do with those?
And then
Yep. Add those numbers up, divide by 2. Should give us what number?
81.
81.5. Okay. And then the mode is the one that appears most often. So in that case, it would be 84. So these three numbers here are going to give you a pretty good idea about the center of this set of data. Average or mean of about 80.75, middle score of about 81.5, and a mode of 84. Any questions on this example? Okay. So some considerations for picking which one you want to focus on. If you have qualitative data, what does it mean by qualitative data?
Like describing kind of.
Yeah, describing, you could think like categories of some kind. But the important thing, qualitative is going to be not numbers. If you do have numbers, then it's going to be quantitative data. That's the key difference there. If you have an outlier, you'll want to use the median. So if you have a really high or a really low value compared to the rest, you'll want to consider using the middle value. instead of the average. The thing with outliers, it won't change your median much, but it can really affect your mean values when you have extremes. But again, outliers unusually large or small compared to the rest of the values. Prime example here, a sample of employee salaries at an accounting firm are listed below. Let's say we look at the mean and median of these. So let me know when you get a value for either one of these. Okay, do we have a value for the mean? $178,833 compared to the middle value for the median, which would be 67,500. So the question here, if someone were to ask you what's the typical salary that someone makes at this accounting firm, which of those do you think is going to be a more accurate picture when looking at the whole group? Bottom one. There's only one salary that's way above this. So this would be considered an outlier in this data set, which is going to make the median a lot more reliable about the true center. Because if we relied on the mean here, 5 out of 6 of these salaries are below this mean. That's not the true center of all of the data values. It's actually the 83rd percentile of all the data values instead of the 50th. Any questions about how to measure center? Okay, the shape of a distribution is just as important. Histograms are usually what we look at for shapes. And there's a couple of things we look at. So the number of modes, which would be the number of peaks. So think something like this. How many peaks? 2. There. The shape, which is typically going to be things that either look like that, or that, or say that. And then variation. For variation, think how spread out. Are the values. So if you have a lot of values that are close together, probably going to be low variation. If you have values that are all over the place, it's going to be high variation. So for number of peaks, the prefix uni means what number? 1. So think 1 peak or maximum value. Bi is the prefix for 2. So bimodal distribution means you're going to have more than 1 peak, in this case 2. If there's 3 peaks, that's trimodal. 4 would be tetramodal. 5 quinmodal. Whatever the prefix is will determine the number of peaks are there. In terms of shapes, this one right here is considered symmetric. And what I mean by symmetric is that I could take a piece of paper and cut it through the center of this. And if I fold the paper on itself, I'm going to get roughly the same shape on each side of where the center is. If it's not symmetric, so one of these other 2 possibilities, then it's going to be skewed. A left skewed graph is going to peak on the right and more gradual descent on the left. And right's the opposite, peaks on the left, more gradual on the right. Now, the easiest way to remember which one is which, if you focus on the tail of each of these, so in other words, where the values are getting smaller, on the first one, you're heading in what direction with that arrow? You're heading left, so that's a left skewed graph. Right skewed, the tail, where it gets smaller, is going to the right. So if you know where the tail is, you'll know which of those skewed situations is there. But the position of the mean and median, if it's symmetric, they're both located in the center. If it's left skewed, which again, that means the tail end is going to the left. Like that. The mean is going to fall to the left of the median. So in other words, your mean might be here, but your median might be here. Right skewed, going the other way, mean will fall to the right of the median. So say median is here. Might be something like this out here. Just because you have a lot of lower values. You can often guess the shape of a distribution of a particular variable. Generally, if you know the trend taking place, you'll have a pretty good idea on the shape as well. Any questions there? Okay, so again, variation. If values are close together, think low variation. The more spread out they are, the more variation that exists, is the idea. And when I say close together, I'm referring to the x values. But when we know the variation, this will tell us how spread out the data is going to be from the center. Which leads us to the second part here, measures of variation, or how spread out values are in data sets. Let's say we look at this example here at your seats. Let's have you find the mean and median of each of those data sets. Okay, do we have some values? How about the mean?
50.
Is 50 for the first one, median 50 as well. How about in the second one? 50, and then the median,
50.
they're all 50. So you might be thinking, okay, that's all right, but kind of weird. But I'm going to follow up here with a question. Is there a data set there that has values that are more spread out than the other one? Which data set has more spread out values?
Set 1.
Set 1. So think more spread out versus data set 2 where they're all close together. So even though we have the exact same mean and median, it's only going to tell us so much. It's only giving us information about where the center is. It's not really telling us much about how far left do they go, how far right do they go on the graph. That leads us to measures of variability or spread. There are two of them, one of which you've seen already, range, which is high minus low values. The other one is called standard deviation. There's a rather fun formula there. Standard deviation equals the square root of the sum of all the deviations from the mean squared over the number of data values minus 1. And I should tell you too, if you're looking up standard deviation anywhere, you might see it denoted like that. Which is the Greek letter lowercase sigma. So if you see any weird O looking things, those are sigmas, and that means standard deviation. And I'll show you how to use this formula here, because this is more of a process here than it is a formula. To figure out the standard deviation, first step is always figure out the mean of the data set. And then we're going to figure out how far or how much it deviates from the mean for every data value. So that's just whatever the data value is minus the mean to find the deviation. You'll do that for every value. Once you do that, square all of them. So if you get the number 5 from this, do 5 times 5 or 5 squared. If you get 10, do 10 times 10 or 10 squared. Once you do that for all of them, then you're going to add up all the values. then divide it by the total number of data values you have minus 1. And then you're going to take the square root at the very end. Following orders of operations with this process. Bless you. You're welcome. I'll be honest with you, this is probably one of the most tedious calculations you'll see in this class. But if you follow the procedure, it's not that bad. But much easier explained through an example. If we need to compute the standard deviation, what was the first thing in our process?
Mean.
Yep, find the mean. So if you calculate the mean of those values,
Twenty.
20? Yep, I agree with that. What was the next step?
Square all of the deviations.
Yep, so we're going to have to find all of the deviations. So the first value is 21 in that list, right? So we'll take that minus whatever the mean is. And that gives us what value?
1.
1. But we're going to do that with all of these. So 25 minus the 20 for the mean gives us 5. 20 minus 20
Yeah.
is 0. 15 minus 20,
Negative 5.
-5. 18 minus 20,
Negative 2.
-2. And then 21 minus 20,
Negative 1.
-1. So taking all of those values, subtracting the mean from them to figure out how far away they are from the mean. Then your next step is going to be squaring each of those numbers that you get from here. So 1 squared would be 1. Yep. 5 squared would be 25. 0 squared would be 0. -5 squared. Super close. When you're typing that in the calculator, make sure that you use parentheses around. Yeah. Not to give you flashbacks of your earlier days in math, but a negative times a negative is a positive. Yeah. Then negative 2 squared, 4. And then negative 1 squared, 1. So that's the third step there. What's the next step?
Add the values from step
So now these values that we got, we are going to add all of these. Values together. What do you get? 56. What are we going to do with that number for the next step?
divided by 6. And then minus
Yep, we're going to divide it by the number of values we have, in this case 6, but minus a 1. So we're really dividing that by 5, which is going to give us what number in the calculator?
11.2.
11.2. Okay, and then the very last step is that we have to
Square it. Do square root thing.
Yep, we're going to take that number that we got and then take the square root of it. If your calculator doesn't have a square root button, you can also put in that number to the 0.5 power. And that would be the same as square rooting it. What number do you get? $3.35. It's just going to be the value of the standard deviation. And if you're paying attention, you probably would have seen this on the next slide anyway.
I literally just said that. I just noticed that.
It's all good. But I figured it was good to walk you through that process there. Just because I know on the third exam, which probably won't be until middle of April, I do know that there's typically a standard deviation calculation on that exam. Any questions there? Okay. You can do a lot of this in Excel. Not saying that you have to, but it is a good way of doing this quickly. But part of the reason that Excel exists is because of statistics, actually. So there are functions that will give you each of those. The only one that can get kind of tricky, when you're in Excel, you might see another function as you're typing the standard deviation one in that looks like this. A P instead of an S. There's an important distinction between them. Going back to chapter 5, the last chapter, when you're dealing with just a portion of the entire group, you were dealing with a what? That starts with an S. I think I heard it. Yeah. So this is actually a sample standard deviation. This one with the P, what do you think the P stands for? Population. Yep. It's almost identical to sample standard deviation, but there's one difference. For sample, we divided by number of values minus 1, right? In that last example. For population, you just divide by number of values. You don't include the minus 1. And those are things that are in the notes down there. Always make sure to enter the data before you use this function. Make sure to include parentheses when using them. And again, if you have an entire population, you'll want to use the population one instead of a sample. It will lead to slightly different answers because of not including that minus 1 when dividing. For our purposes, we're probably going to focus just on sample. But if any of you have to take a full statistics class at some point, then you'll probably have to do population as well. It'll just kind of depend on your future program path on that one. Any questions there? Okay, the last thing in this chapter is, okay, we dealt with standard deviation, but what exactly does it mean? What is it telling you? If we know what the mean and the standard deviation are, we're going to have a pretty good idea of where the rest of the values are going to be. There is a theorem denoted as Chebyshev's theorem. Basically, Chebyshev was this dude who came up with the idea that at least 75% of all data values will fall within 2 standard deviations of the mean, and at least 89% of all data values will fall within 3 standard deviations of the mean. Anyone have any idea where Chebyshev is from with that name? Okay, think Vladimir Putin. If you know where he's from.
Is it Russia?
Russia. Yep. Yep, so Chebyshev was this Russian dude who came up with this theorem here. But I'll give you an example of what it means here before we look at this. Going back to the standard deviation example that we did here, we figured out that it was 3.35, right? And we figured out that the mean was 20. So I'm just going to take those values real quick, just so you can see what it's talking about here. So mean is 20. And we said standard deviation was 3.35. What would 2 of these standard deviations be if you had to multiply that by 2? $6.7. So what he's saying here, take your mean, which in this case is 20. If you add 6.7 to it, that's going to be 26.7, right? If you subtract 6.7 from the 20, 13.3. So basically what he's saying is that at least 75% of the data values that we had in that example are going to fall between 13.3 and 26.7. I'll just get those values back here real quick. So it was 21, 25, 20, 15, 18, and 21, right? Are at least 75% of those values between 13.3 and 26.7? Are there any that aren't? They all are, right? So you can have more than 75%, but you're going to have at least that percent of values that fall within that range, within 2 standard deviations. And then applying that same idea, if we did 3 standard deviations, would 3.35 times 3 be? 10.05. So we do the same thing here. Mean of 20. If you add that to your mean, you would get what value? 30.05. And then if we subtract it, 9.95. So then he's saying at least 89% of values will fall between the 9.95 and the 30.05. Any questions on what that means here or what it can tell you? Okay, last example for the night. Delivery service has collected data on the number of deliveries made per week for 500 drivers. The mean was 250 and the standard deviation was 10. So according to Chebyshev, at least 75% of drivers fall within how many standard deviations? If it's 75%? According to his theorem.
$230 and $270.
You have 2 standard deviations, which would be 20 deliveries, right? So off from the 250 would be 230, and then on top of it would be 270. And then at least 89% of drivers would fall within 3. So that would mean 220 and 280. Because that would be 30 deliveries. So the last question, would you be surprised if a driver reported making 400 deliveries? Yeah, I would be. Because 89% are going to fall between 220 and 280. 400 would definitely be an extreme from that. Okay. Any questions on chapter 6? Okay. So we'll stop there for tonight. Looks like I kept you guys over a minute, so my apologies.
It's okay.
Made a lot of good progress tonight, though.